Hey everyone, welcome back to my channel Beaker and the Board. So in my previous 5 videos I have discussed regarding the reduction reaction, oxidation reaction, the difference between valency and oxidation state, and also about the rules that you need to know regarding the calculation of oxidation state. Please do not jump into the calculations directly. You need to know the rules and then you can do them. So, let's start today's class. I will initially start with the easy examples and then I will continue with the harder ones. Please continue to watch till the end so that you get to understand everything in details. Okay. So my first example is regarding the calculation of oxidation state for carbon in carbon dioxide. Remember, whichever element's oxidation state is asked to calculate, that element is taken as X. Oxidation state of element whose oxidation state is to be calculated is taken as X. So here I consider X as the oxidation state of carbon. So X into 1 because only one carbon atom is there, plus minus 2 into 2 because there are 2 oxygen atoms, minus 2 into 2 is equal to 0. I hope you have gone through the previous video and I have told you that oxygen can have many oxidation state. Oxygen can exist as oxide, which we say as O minus 2. Whenever we say O minus 2, it is oxide. Whenever we say O2 2 minus, O2 2 minus, or you can say O minus 1, then that will be called peroxide. That will be called peroxide. And whenever we say O2 minus, then we say that as superoxide. O2 minus is called superoxide. That means each oxygen atom will be having an oxidation state of minus 0.5. Now, here in carbon dioxide, oxygen, as the name itself suggests, oxygen is existing as oxide. So, minus 2 is the oxidation state. We are having 2 oxygen atoms, so into 2 is equal to 0 because carbon dioxide is a neutral molecule. No charge has been assigned to it and we know all molecules are neutral. So, X comes to be plus 4. That means in carbon dioxide molecule, the oxidation state of carbon is plus 4. Now let's choose another example. Say suppose if I want to calculate the oxidation state of oxygen in hydrogen peroxide, H2O2 is the molecular formula of hydrogen peroxide. The structure is somewhat like this: OO, each oxygen bonded to one hydrogen atom. Whenever you find this kind of bond, OO single bond, whenever you find this kind of bond, remember that is called a peroxo bond. Peroxo bond. We are asked to calculate the oxidation state of oxygen. So we will take oxygen to be X. Hydrogen is bonded to more electronegative element. So it will have a plus 1 charge. If you consult my previous video, you will get to know that whenever hydrogen is bonded to more non-metallic element or more electronegative element, it bears plus 1 oxidation state. So plus 1 into 2 because there are 2 hydrogen atoms, so plus 1 into 2 plus oxygen atom is X into 2, X into 2 which is equal to 0. If you calculate, then X comes to be minus 1. X comes to be minus 1. That means in hydrogen peroxide, not only in hydrogen peroxide, in any peroxide compound, whenever you find this kind of OO single bond, oxygen double bond will be O2. Double bond is O2 molecule. But if it is single bond, then it is peroxo bond. In every peroxo compound, each oxygen atom bears -1 oxidation state and hydrogen atom bears +1 oxidation state. I hope it is clear till this. Now let's move to another example. Say suppose if I want to calculate the oxidation state of boron in sodium borohydride. Sodium borohydride. Hydride, I hope you remember that in hydride compounds, whenever hydrogen is bonded to a metal or when hydrogen is bonded to less electronegative element, then it is called hydride and hydrogen bears -1 charge. Sodium borohydride. Both sodium and boron are less electronegative than hydrogen. Hydrogen is more electronegative than both the other elements, sodium and boron. So let's take boron as X. Sodium has only one oxidation state, that is +1. Sodium, potassium, all these are alkali metals. They have only one oxidation state, that is +1. So +1 into 1 because there is only one sodium atom, plus boron X into 1 because there is only one boron atom, plus hydride means -1 into 4 is equal to 0. That means +1 plus X minus 4 is equal to 0. X comes to be +3. That means in sodium borohydride, the oxidation state of boron is +3. The next example is, let's take an example of an ion. Let's take for phosphate PO4 3-, phosphate ion PO4 3-. Now if suppose I am asked to calculate the oxidation state of phosphorus in phosphate. So let's take phosphorus as X. So X into 1 because only one phosphorus atom is there, plus oxygen will be -2 into 4 because there are 4 oxygen atoms. Each oxygen atom bearing -2 charge is equal to, now we can see that phosphate is a complex ion. It is a complex ion. What is the meaning of that? Complex ions means that there are more than one element. Here we are having two types of element. We are having phosphorus and we are having oxygen atom. One phosphorus and 4 oxygen atoms together make phosphate ion such that they carry a total of -3 charge. So X into 1 plus -2 into 4 is equal to -3. On the right hand side, you always put the total charge of the species given to you. If you are given a molecule, you will give equal to 0. If you are given a cation, then you will give on the right hand side, you will provide the charge of the cation. If it is +2, then equal to +2. If it is +3, then equal to +3. If it is an anion, like here phosphate, it is -3. So it is -3 on the right hand side. So X -8 is equal to -3. So in phosphate ion, X comes to be +5. The oxidation state of phosphorus is +5. Now the question is, how is it possible? See, whenever you are given to calculate the oxidation state of one element in a heteroatomic molecule, always remember that the element which is more electronegative will carry a negative oxidation state and the element which is less electronegative will bear a positive oxidation state. Phosphorus is less electronegative, oxygen is more, so oxygen carries a negative oxidation state, and phosphorus being less electronegative carries positive oxidation state, and it is +5. Now the question is it possible? How can phosphorus have +5 oxidation state? You will read this and understand in details in variable covalency. I'll provide you some lectures for that, but till now it is possible to explain through the electronic configuration. Phosphorus has an atomic number of 15. So the electronic configuration comes out to be 1s2, 2s2, 2p6, 3s2, 3p3, or you can also write KLM, that is 2, 8 and 5. 2, 8 and 5. Now see, if you remove the 5 electrons from the last shell, if the 5 electrons, that means if this 3 electrons minus 3 electrons from 3p and minus 2 electrons from 3s, that means if 5 electrons are lost, then it becomes Kl28 configuration. That means this is the configuration of neon, the noble gas, which is stable. So that means it is possible to have 5 plus 5 oxidation state for phosphorus. Since it is less electronegative, so it has plus charge, and after it loses 5 electrons, then what happens? It achieves the noble gas configuration. So it is definitely possible that phosphorus can have plus 5 oxidation state. Now let's come to a little different example. Say for example, I want to calculate the oxidation state of sulfur in H2SO5. H2SO5. The common name of this molecule is Carrose acid. This is called Carrose acid. Carrose acid. Now, if you are asked to calculate the oxidation state of sulfur, let's see what happens if we choose the oxidation state of oxygen as -2. So it is +1 into 2. Hydrogen is less electronegative than both sulfur and oxygen, so it is +1 into 2, plus sulfur. Sulfur, let's take this as x into 1. X into 1, we have to calculate for that. Now it is -2 into 5. -2 into 5 is equal to 0. So what is the oxidation state for this? The oxidation state for this comes to be +2 plus x minus 10 is equal to 0. So x comes to be +8. That means in Carrose acid, the oxidation state of sulfur on simple calculation comes to be +8. That means if you choose -2 oxidation state for all the oxygen atoms, there are 5 oxygen atoms, of which all the 5 oxygen atoms carry -2 charge. Then the oxidation state comes to be +8. Now the question is it possible? Is it possible for sulfur to have +8 oxidation state? What to do for that? Let's check it. Let's verify it. See, for sulfur, the electronic configuration is 16. So atomic number is 16. So electronic configuration comes to be neon, then 3s2, 3p4. 3s2, 3p4. That means when sulfur loses 6 electrons are lost. That means 2 electron lost from 3s and 4 electron lost from 3p. If the 6 electrons are lost from the last shell, then sulfur achieves a noble gas configuration. The configuration of the nearest noble gas, that is neon. That means sulfur at the maximum can lose 6 electrons. the maximum oxidation state for sulfur atom is +6. The maximum oxidation state for sulfur atom is +6. It can be +2, it can be +4, it can be +6, but it cannot be +8. That means my calculation, though it is correct, +8, my calculation is correct, but the +8 oxidation state for sulfur in Carrot's acid is not possible. Sulfur can never achieve +8 oxidation state. The maximum oxidation state possible is +6. So what to do for that? Is my calculation wrong? No, my calculation is correct. Then what to do for that? Because it cannot be +8. It can be +6 or less than that, but not more than +6. That means for that we need to know the structure. So what happens? The structure for Carrot's acid is somewhat like this. There are 2 hydrogen atoms. See, I hope you have understood. All the chemical formula is completely satisfied here. We have 2 hydrogen, so H2. We have 1 sulfur, so S. And we are having 5 oxygen atoms. Sorry, we need to put another one. We are having 5 oxygen atoms. H2SO5. So, now what to do? So, we can very clearly see that we are having a peroxo bond here. Oxygen-oxygen single bond. Remember, peroxo bond is a single bond between 2 oxygen atoms. When 2 oxygen atoms are bonded to each other through a single bond, that is called a peroxo bond. But oxygen is always bivalent. It has to form 2 bonds. That means, see, even in the peroxo bond, each oxygen has 2 bonds. Each oxygen must be having 2 bonds. Now see what to do. So, each oxygen in the peroxo bond, each oxygen will be having -1 charge. You already know it. In peroxo bond, each oxygen atom carries -1 charge. Hydrogen will be carrying +1. Each hydrogen +1. Let's consider sulfur as X, and the other oxygen atoms will be -2. Now calculate it, you will get the answer. See, for hydrogen we are having 2 hydrogen, so +1 into 2. Plus we are having 1 sulfur, so X into 1. Then we are having 2 peroxo oxygen atoms, so -1 into 2. Plus we are having 3 oxygen atoms which are -2. That means -2 into 3 is equal to 0, because at the end it is a molecule, it is neutral. So +2 plus X -2 minus 6 is equal to 0. So that means X comes to be, just a minute, X comes to be +6. X comes to be +6. That means in Carrot's acid, there is 1 peroxo bond. This is the structure of Carrot's acid. I have already shown in the diagram. Please copy down. In Carrot's acid, sulfur atom has different kinds of oxygen atom. 3 oxygen atom existing as -2 and 2 oxygen atom existing as peroxo. That means there is a peroxo bond. So in Carrot's acid, the oxidation state of sulfur is +6. Let's take another example. Say if I choose +6 oxidation state is definitely possible. I have shown you. Now let's see for another one. It is H2S2O8. H2S2O8. This is called, the chemical name, the common name is Marshall's acid. The chemical name of this acid is Marshall's acid. You have heard of sulfuric acid, you have heard of sulfurous acid. So just like that, Marshall's acid, Caro's acid are also various oxy acids of sulfur. Sulfur has oxygen atom in it, oxy acid. All of them are acidic, but they are oxy acids. Now the chemical formula of Marshall's acid is H2S2O8. So again, let's start. If I choose oxygen atom to be -2, let's see. So hydrogen +1 into 2, +1 into 2, 2 hydrogen atoms. Sulfur, let's take sulfur, X into 2, plus oxygen is -2 into 8 is equal to 0. So what happens? +2 plus 2x minus 16 is equal to 0. That means 2x is equal to 14. So x comes to be +7, which is again not possible. I have already instructed that sulfur, you can verify it. Sulfur cannot have oxidation state more than +6. The maximum oxidation state is +7. It can have less than +6, but not more than +6. +7 is more. So +7 oxidation state for sulfur is not possible. So that is why again we need to know the structure. What happens? The structure is somewhat like this. See, we cannot change the chemical formula. If it is having 2 hydrogen, there will be 2 hydrogens only. If there are 2 sulfur, there will be 2 sulfur atoms only. You cannot change the number of atoms according to your convenience to bring the suitable oxidation state. So it is somewhat like this again. See, we are already having 2 sulfur, 2 hydrogen, and oxygen we have given 4. The next one is something like this. This is the structure of Marshall's acid. So what happens? Again we are having peroxo linkage, oxygen-oxygen single bond. But see, on both the sides, all the oxygen atoms are bivalent. Every oxygen atom must have 2 bonds with it. Whether it is peroxo oxygen or superoxo oxygen or oxide oxygen, doesn't matter. Oxygen is always bivalent. It will always have 2 bonds with it. Either it will form double bond, or if it forms single bond, then 2 single bonds on 2 sides. It must have 2 bonds. Every oxygen will have 2 bonds. Now let's start the calculation. Let's take sulfur to be X. And the oxidation state of sulfur is X. Hydrogen will be again +1 because it is less electronegative than the other atoms. Other than the peroxo oxygen atoms will have -1 oxidation state. The other oxygen atoms will have -2 charge, -2 oxidation state. Now see, if you calculate what happens, let's see. We are having 2 hydrogen atoms, each having +1 charge. So +1 into 2, plus we are having 6 oxygen atoms, each -2 into 6. Each oxygen atom having -2. 6 oxygen atoms are there having -2 oxidation state. Each 6 are there, -2. So what happens? -2 into 6. Then we are having 2 peroxo oxygen atoms. So it is -2 into 2, -1 into 2. Plus we are having 2 sulfur atoms. 2x is equal to 0. Now see the calculation, it is plus 2 minus 12 minus 2 plus 2x is equal to 0. So the net calculation comes to be x is equal to plus 6, which is definitely possible. That means, just remember, the maximum oxidation state for sulfur is plus 6. It cannot be more than plus 6. It can be less but not more. Let's see another example. See, for example, if I choose a simple one, sulfur dioxide, SO2. Sulfur dioxide. Do I need to have peroxo bond here? No. We can verify from the calculation itself. If I take sulfur to be x into 1. If I say oxide, sulfur dioxide, the name itself says oxide. So that means minus 2 into 2. Now let's see whether the calculation shows the oxidation state to be more than plus 6. If it is more than plus 6, then I cannot take oxygen to be minus 2. It should not be more than plus 6. It can be less than that, but not more than that. So what is the value? X comes to be plus 4, which is possible. It is less than plus 6, so it is possible. Up to plus 6, for sulfur atom, up to plus 6 is possible. Now, the next one is, let's choose a little difficult one. Say for example, if I want to calculate the oxidation state of, say, chromium in chromium pentoxide. Suppose this is the example. Chromium pentoxide. Now you may get confused. Chromium pentoxide. So it is an oxide. Let's see if chromium is given to be calculated. So it is x into 1. X into 1. And if I choose all the oxygen atoms to be minus 2. Minus 2 into 5 is equal to 0. So x comes to be plus 10. Is it possible? Let's verify. Is it possible for chromium to have a plus 10 oxidation state? If it is possible, we can definitely go with it. If it is not possible, then something is wrong. We need to know what is the mistake. Now, before knowing the mistake or before verifying it, we need to know the electronic configuration. The atomic number of chromium is 24. So the electronic configuration is 1s2, 2s2, 2p6, 2p6, then 3s2, 2p6 it is, then this 3s2, 3p6, 3d, 4s, 4s1, 3d5. Chromium shows an exceptional electronic configuration. So it is 3s2, 3p6, 3d5, 4s1. See, up to this, up to 3p6, isn't it having 18 electrons? 2 plus 2, 4, 4 plus 6, 10, 10 plus 2, 12, 12 plus 6, 18. That means up to 3p6, it is 18 electrons. That means argon. Then it is 3d, 4s, 4s1, 3d5. Now see, if chromium loses 6 electrons are lost, minus 6 electrons, then what does it become? It gets the electronic configuration of argon. Do you need to lose any more electrons? If it has already achieved the noble gas configuration, why will it lose electrons anymore if it is already stable? Argon is already stable, it is already a noble gas. Something which is already stable, will it prefer to lose its stability? No. So that means argon, after losing 6 electrons, when chromium atom loses 6 electrons, it gets the electronic configuration of argon. Chromium plus 6 gets the electronic configuration of argon. That means it is just like that. Chromium plus 6 has the similar configuration of argon. So the maximum oxidation state for chromium is plus 6. It cannot be more than plus 6. It cannot be plus 7, plus 8, nothing. It can be less than plus 6 or plus 6 but not more than that. That means this calculation plus 10 is wrong. You cannot consider all the oxygen atoms to be minus 2. So what is the configuration then? It comes to be something like this. Chromium, double bond oxygen, and we need to satisfy the chemical formula. This is the structure. See, I have given one chromium atom and there are 5 oxygen atoms. CrO5. All the oxygens are not oxide. There are 2 peroxo bonds. See, oxygen, oxygen, single bonds are there. There are 2 peroxo bonds. You cannot consider all the oxygens to be oxide. But remember, all the oxygens must be double bonded. If double bond, then it is okay. If it is single bond, then 2 single bonds on both the sides. See, each oxygen is having 2 bonds. All the oxygen atoms are having 2 bonds. Now what happens? If I choose chromium to be X, what should I do for the peroxo oxygen? The peroxo oxygen will be minus 1. Each peroxo oxygen will be minus 1. And the other oxygen atom will be minus 2. Peroxo means it is something like this, OO single bond. Whenever 2 oxygen atoms are single bonded to each other, then it will be peroxo bond. So what happens? X into 1, chromium atom, only one chromium is there, so X into 1. One oxygen existing as oxide, minus 2. So minus 2 into 1. And we are having 4 peroxo oxygen atoms. So minus 1 into 4 is equal to 0. So what happens? X minus 2 minus 4 is equal to 0. So X comes to be plus 6, which is definitely possible. That means if you consider all the oxygen atoms to be minus 2, an invalid oxidation state of plus 10 comes, which is not possible. That means the actual structure of chromium pentoxide is somewhat like there are 2 peroxo bonds. There are 2 peroxo bonds. Each oxygen having 2 bonds. If it is double bond, then it is okay, 2 bonds. If it is a single bond, then 2 single bonds on both the sides. Peroxo bond, it is plus 6. In chromium pentoxide, it is the oxidation state is plus 6. Now, if I consider, let's choose another example. Say for example, if I want to calculate the oxidation state of phosphorus in pyrophosphoric acid, the name is something like this, pyrophosphoric acid. And what is the formula for that? It is H4P2O7, pyrophosphoric acid. You are asked to calculate the oxidation state of phosphorus. So let's start now. Hydrogen is less electronegative than both oxygen and phosphorus atom. So it is plus 1 into 4. Plus 1 into 4. Plus phosphorus 2x. We are asked to calculate for phosphorus and there are 2 phosphorus atoms, so 2x. Plus oxygen minus 2 into 7. Let's start with minus 2 consideration. If it is within the limit, then it is okay. Otherwise, we have to go for the peroxo, is equal to 0. So what happens? It is plus 4 plus 2x minus 14 is equal to 0. So x comes to be plus 5, which is possible. The maximum oxidation state for phosphorus is plus 5. Now why do you think so? I have already shown you while explaining you the oxidation state for phosphorus in phosphate PO4 3-. I have already explained. Please see that. In the next class, I will come with few more examples of calculation of oxidation state, and they will be harder than this. Please stay tuned and follow my next class. Thank you everyone.